All right, so we are now looking at exponential growth and decay. An exponential growth and decay predicts the behavior of variables, grow or decay at a rate proportional to their size. So for exponential growth and decay models, we can see we have some formulas here. Remember that f of t is going to be the same thing as a. This is a sub naught, which is going to be our original starting point, e to the k times t. If k is greater than 0, the function models the amount or size of a growing entity. So if our exponent is positive, then it's going to go up. If our k is less than 0, it will make our exponent negative and it will go down. So let's go look at an example. So for example 1, the population of country A is given in the model of A equals our equation in millions in T years after 2010. What is the population in 2010 and what was the population or what will the population be in 2014? All right, so let's write this out. So we are in 4.5. So example 1, we have A is equal to 127.3 e to the negative 0.006 t. Watch out for those zeros. For part A, we're looking at, and this is after 2010 is our model. But on part A, we're asked, what about in 2010? Well, in 2010, the years that have passed are 0 years, and so t is going to be equal to 0. So we have A is equal to 127.3 e to the negative 0.006 times 0. So A will be equal to 127.3. This ends up being e to the 0 power, and anything to the 0 power is 1. So we end up with 127.3 million, because this will all become 1 as it's raised to that 0 power. Now for part B, we are asked about 2014. So what will the population be in 2014? So if we take 2014 and then subtract our original year of 2010, we end up with 4. So A is equal to 127.3 e to the negative 0.006 times 4, which means we have 127.3 e to the negative 0.024, and that gives us a value of 124.28 million. So notice from this one to this one, what happened? We actually decreased. So in 2014, 4 years later, we had less of our population, and that is because we have a negative exponent. So it is a decreasing value. All right, let's look at example 2. So in example 2, we have the population of country B is given in the model in millions after 2007. So what will the population be in 2010? What will it be in 2020? And when will the population be 47 million? So we are going to start by looking at our equation. So I'm going to write that first. So our equation is A is equal to 31.5 e to the 0.019 t. And this is in 2000 so after 2007. So for part A, we are looking at in 2010. So in 2010, we are looking at what is our t? Well, we have to subtract our 2007 and get that our t is going to be equal to 3. So we'll have A is equal to 31.5 e to the 0.019 times 3, which will get us 40.33 million. Now for part B, we are looking at the year of 2020. So if we take 2020 and minus our original of 2007, we will get our t is equal to 13. So A is equal to 31.5 e to the 0.019 times 13, and that will get us 40.33 million. So we made an oops. Looking at all of my notes here, sorry about that. So this is actually going to be 33.35 million for the first one. For part B, we'll get 40.33 million. Sorry about that. So be careful when you're note taking. Alrighty, so part C, it's asking us when will the population be 47 million? Well, 47 is going to be our accumulated value, so that's going to be our A. So we have that A is equal to 47. So we will have 47 is equal to 31.5 e to the 0.019 t. We're going to divide both sides by 31.5. So we'll have 47 divided by 31.5 is equal to e to the 0.019 t. Well, we need to take the natural log of both sides here in order to solve for t. So we'll have the ln of 47 divided by 31.5 is equal to the ln of e to the 0.019 t. Remember that ln and e undo each other, and so and by our natural log properties, we will end up with just the exponent. So the ln of 47 divided by 31.5 will be equal to 0.019 t. So I'm going to finish this one right up here. So I'm going to rewrite that. So 47 over 31.5 equal to 0.019 t. So now I need to divide both sides by 0.019. And we'll have the ln of 47 divided by 31.5 divided by 0.019 is equal to our t. So t will be equal to approximately 21 years. So that's how long. This is the how long part, 21 years. But they asked us to tell them the when. So this is how long. The when part, we will take our original year of 2007 plus 21 and get 2028. So this would be our final answer, would be in 2028. So this is one of those problems where you're going to have to answer a couple of things. Alrighty, so the next thing we're going to look at is example 3. And in example 3, we are looking at completing a table for population growth. So in 2005, the population in millions is this. Projected 2024, the population will be this. And we're looking for the projected growth of K. So let's go look at what we need to know. So for example 3, we are looking to use the formula A is equal to A sub naught e to the k times t. So on the given information, our projected growth is our A, and that is 38.3 in millions. our A sub naught was what the population was in 2005, which is 43.5. And our T, we're going to find by the years. So we are starting in 2005 and going to 2024. So 2024 minus 2005 will get us 19 years is the change in time. So let's take our formula and plug in what we know. So using our formula here, we'll have 38.3 is equal to 43.5 e to the k times 19. Now we'll divide both sides by 43.5. So we have 38.3 over 43.5 is equal to the e, and I'm going to change that to 19k instead of k19. It's multiplication, so it does not matter. So now we'll take the ln of both sides. So ln of 38.3 over 43.5 is equal to the ln of e to the 19k. Now remember, through those logarithmic properties and the natural log properties, that the ln and e, when we have that, it will just leave us with the exponent. So we have the ln of 38.3 over 43.5 is equal to 19k. Now we need to divide both sides by 19. So we have the ln of 38.3 over 43.5 divided by 19 is equal to our k. So our k is approximately negative 0.0067, which is what we would expect as far as positive or negative because the population is going down. So we should have a negative exponent. It went down from 43.5 to 38.3. All right, let's go on to our next problem. So carbon-14 decays exponentially with a half-life of approximately 5715 years. So we have about carbon dating with the Dead Sea Scrolls. In 1947, the Dead Sea Scrolls contained 76% of their original carbon-14. To find their age in 1947, substitute 0.76 A sub naught for A in the formula that is right there. All right. So let's go look at that. So for example 4, scooch this up just a little bit. We have A is equal to 0.76 times A sub naught. So remember, we're using our original formula there. They gave us a formula to use of A is equal to A sub naught times E to the negative 0.1230121t. So make sure you get enough zeros in there. So our A is actually equal to 0.76 times A sub naught. So 0.76 A sub naught is equal to A sub naught e to the negative 0.000121t. So we can divide both sides by that A sub naught, which is also known as A sub 0. So we end up with 0.76 is equal to e to the negative 0.000121t. Now we can take the ln of both sides and get the ln of 0.76 is equal to the ln of e to the negative 0.000121t. And the ln and e undo each other again, we end up with just the exponent. So the ln of 0.76 is equal to the exponent of negative 0.000121t. Divide by negative 0.000121. so that we get t by itself. So the ln of 0.76 divided by negative 0.000121 is going to be equal to our t. And so t is equal to 2268. So 2,268. So if we're looking at today, which is in 2020, is when I'm recording this. So if we're looking at that for today, we would have our 2268 plus however many years have passed. So right now we're looking at 2020 minus 1947, which would be 2268 plus 73, which will get us 2341. So we found the value for RT, so 2341 years. All right, so let's go look at another example. We're looking at example 5. So for example 5, we're looking at a couple other little things first. We have the half-life of a substance as the time required for half of a given sample to disintegrate. To find a half-life of a substance, substitute a sub naught over 2, because it's half the life, in the formula for A. In the formula, A equals a sub naught e to the kt. So we're going to use a sub naught over 2 this time. So completing the table for the half-life, the decay rate is K, so it's 5.3% per year. You have to change this to a decimal and understand that it is a decay rate, so you have to put a negative sign in front of it. So let's go work at this problem. So again, we have A is equal to a sub naught over 2, and we are given that K is equal to the negative 0.053. Our original equation is A is equal to a sub naught e to the kt. So plugging in our A, we have a sub naught over 2 is equal to a sub naught e to the negative 0.053 times t. So again, dividing by a sub naught, the a sub naughts will cancel out and we'll end up with 1 over 2 is equal to e to the negative 0.053t. And now we'll take the ln of both sides. So the ln of 1/2 is equal to the ln of e to the negative 0.053t. And again, using those properties of natural log, we're going to find that we end up with the exponent over here. So the ln of 1/2 is equal to negative 0.053t. And we're going to divide both sides by negative 0.053. So the ln of 1/2 divided by negative 0.053 is equal to our t. So our t is equal to 13.1.